Hello, this is Andrew with WS Tyler. How may I help you today?
Yeah, so this is Andrew. I was that one guy who ordered the mesh from you guys.
Ah, yes, the mesh. How could I forget? Those were good times.
The mesh is just broken, so it's not our fault. So how are you guys gonna fix this?
Oh, gosh, I'm sorry to hear that. Did it arrive damaged?
No.
Okay, did it not filter the particle range you were looking for?
No, actually, worked great, actually.
And what seems to be the problem?
When we dumped it in sulfuric acid, it kind of just snapped from the pressure.
So sulfuric what now?
Yeah, our process uses sulfuric acid.
You didn't... What alloy are you using again?
Oh, you know, 304 stainless steel.
That's not rated for sulfuric acid.
The 304 is corrosion resistant.
Yeah, but not that corrosion resistant. What? And that is why alloy is important. You see, you might know your specs, the particle range, the weave type you need, even the pressure in your system, but if the alloy isn't right for the environment you're putting your mesh in, then there are gonna be some problems. Choosing the right alloy could mean the difference between ultimate success and ultimate defeat. So, what exactly is alloy? Welcome to my true desk within the void. Okay, so a metal alloy is when you take two or more elements from the periodic table and you combine them to make a material that has superior properties. It's like a super metal. And these elements can make an alloy that has superior strengths and resistances. The superpowers revealed. So the main alloys that are used for woven wire mesh are stainless steel, brass, copper, nickel, aluminum, Inconel, and Hastelloy. Just to name a few possibilities. That's technically not all of them. Mesh can be made out of basically any alloy, but those are the most common, and some of those are pretty rare for woven wire mesh. So, and to complicate things further, there are slight variations of the same alloy. Like for stainless steel, you'll often use a 304, a 316, or a 430 grade. And each of these stainless steels have their own unique strengths and weaknesses. But that's only the beginning. So, the stainless steel category has several grades within the 300 and 400 series. And there's kind of more than just 300 and 400. And that basically goes for all the metal alloys that I mentioned, but I don't think we want the episode to be 2 hours long, so what we're gonna do instead is we're not gonna look at all the possible alloys out there. What we're gonna do is look at the properties that you want in your alloys. So the main properties that most woven wire mesh users are looking for are corrosion resistance, strength and hardness, heat resistance, electrical conductivity, weight and density, magnetic properties, and cost. Oh yeah. Now that's technically not everything. But that's most of what you're going to be looking for, and this is going to take long as it is. So let's get cooking. We're going to be going through each and every one of these properties and what the main industries that these properties are featured in. This is a really big one. Corrosion usually happens when wire mesh is exposed to chemicals. Like a supervillain. I'm so sorry, I'll stop now. Corrosion can just happen when it's exposed to the natural elements, like when metal just simply rusts, but that's not the only form of corrosion. You can also have tarnishing, which is when the metal begins to blemish and gets this dull splotchy pattern all over it. Like, look at this thing. This is, like, we didn't dress this up or anything. This is just actual use. That's crazy. But it's actually not really harmful to the mesh. There's actually situations where the tarnishing can look pretty cool, actually, but for woven wire mesh, disgusting. Then there's pitting corrosion, which is kind of like just normal rust, except it's kind of localized on very specific spots of the mesh. If the pitting continues, it can create craters or holes that go deep into that localized area. Not very good. So the main industries that definitely don't want corrosion is chemical processing plants. Shocker, I know. They could be processing gas and oil, plastics, agricultural sprays, anything where the base elements of their products are highly acidic or corrosive. So an alloy that would be perfect for these type of environments is Hastelloy. Hastelloy is generally made out of nickel, molybdenum, chromium, tungsten, and sometimes cobalt. And literally all of these metals majorly enhance corrosion resistance, except cobalt, which is more heat and strength. But nickel in general is just really corrosion resistant. The molybdenum protects it from those really intense chemicals that make pitting and crevice corrosion a thing. The chromium forms an oxide layer that protects the mesh even more. And you want even more corrosion resistance? Boom, tungsten. There. It is literally in its makeup to not care about chemicals. Now, I just want to caveat this. When you're selecting an alloy for an industry like this, yes, you need something that is highly corrosion resistant, but you also need to consider all the other factors that I mentioned before. Most industries will not just be worried about corrosion only. They'll be worried about heat and conductivity, strength, everything. Speaking of,
Strength and hardness.
everyone wants their mesh to have high strength.
Unless you're a milk drinker.
What properties do you need to be a milk drink high strength alloy? The two biggest factors you're looking for are yield strength and hardness. Yield strength is all about the mesh just not generally deforming or bending or just basically losing its shape. Pretty good. The higher the yield strength, the more likely your mesh can be used long and true. This is not an example of that. Yeah, unless. No, it's just going the other way now. I've heard it just like, kind of scary. Yeah, anyway, and if your mesh has a high hardness rating, you can throw anything at that mesh and it'll just say, "Is that all you got? Go on, kill me. Go on, do it. Kill me." And not a scratch or a dent or any kind of abrasion for that matter will be a problem as a best case scenario, of course. Please forgive me, I'm so sorry. These two are the most important because they're all about maintaining the original shape of the mesh, which means it stays accurate. I mean, honestly, that looks pretty good. Other than that, ductility is important, which means when it deforms, it'll take a lot, and I mean a lot to take. A lot of pressure before it like snaps or breaks. And then fatigue strength can be pretty good too. Since most mesh is made to be reused, it's good to know that it can withstand the loading and unloading process and intense cleaning and reloading process without it being, deformed or scratched or, stuff like that. But that usually comes with the values of strength and hardness just as a default. Now, an industry that really, really needs high strength is the aerospace and aviation industry. There's a lot of stress that gets put on those planes, especially in harsh weather conditions, and you really don't want the mesh to just snap. That would be so bad, especially within the harshest conditions within the plane. Like for combustion chambers that manage airflow and fuel inside jet engines. Something really bad could happen in there if that mesh failed. Which is why we highly recommend your mesh be made out of Inconel. Andrew, why do you keep naming off these weird alloys? What about stainless steel? What about aluminum? Well, the aviation and aerospace industries use those alloys as well. Aluminum's everywhere on a plane because it's just really lightweight. But don't use aluminum in a jet engine's combustion chamber. We're gonna want to use Inconel for that one. Anyway, Inconel is pretty comparable to Hastelloy when it comes to its corrosion resistance, Hastelloy still being better. But Inconel is made out of nickel, chromium, iron, molybdenum, niobium, cobalt, and some other trace elements. Now, since I already went over some of those elements, I'll just stick with the new ones. Introducing iron. Iron is really strong. It's very strong. It adds a lot to its structural stability. And niobium also adds to its strength, especially in those precarious, extreme high altitude environments. And I kind of mentioned cobalt, but it basically adds extra strength when under high temperature conditions. Speaking of high temperatures, if things are heating up, what will your mesh do? Hopefully have a high melting point, great thermal stability, great heat distribution, and creep resistance. What are those? Oh, hey, didn't see you there. So a high melting point is pretty self-explanatory. At extreme high temperatures, you want a high melting point for your mesh so your mesh doesn't literally melt. And thermal stability is all about maintaining its strength even when those processes get a little heated. Heat distribution is when your mesh distributes the heat evenly throughout it, which makes it way less likely for breaks to happen or deformation in very specific areas. And creep resistance is kind of like the beginning stages of melting, but it doesn't melt all the way. Sometimes it'll just deform to the point where the openings aren't exactly accurate anymore. So high temperature resistance is all about the mesh not melting and basically keeping its strength through hot environments. But wire mesh literally melting? What industry is even worried about mesh melting? That's a little dramatic. Nuclear power plants, like the reactor core of a nuclear power plant. They need that precision because everything in there is precise, because if it's not, then we all die. That's a bit of a hyperbole. It's actually pretty incredible how safe nuclear power plants are. But woven wire mesh is everywhere in those reactors because they need to stand up to that heat. So what alloy do they use?
Hang on. Trying to get this darn thing to focus. There we go.
Inconel. Andrew, you already talked about Inconel. Where the heck is stainless steel? We want stainless steel in our nuclear reactors. Give us stainless steel. And this is where I make the stainless steel fans around the world very sad. I'll be getting the stainless steel, I promise. But if these episodes were in any way an indicator, we kind of deal in the extremes of woven wire mesh and what they can be pushed to. And stainless steel doesn't really fit an extreme category. It's got great heat resistance, it's got great corrosion resistance, but not really enough to deal with those extreme environments that we've been talking about. But if it's any consolation, if you can't use Inconel for your nuclear reactor, well then you'd use Hastelloy, but then you would use stainless steel. So third place, still pretty good. Unless you're counting the really, really rare alloys that are actually better than Inconel, but nobody really uses because they're like super expensive and actually really rare, then yeah, third place. There's always a bigger fish. Anyway, since I already talked about Inconel, I'll just simplify it for you. Basically, any base element that's used to make something more corrosion resistant will also make it more heat resistant. So, did you know large amounts of heat can actually generate electricity? Segue. If you need your woven wire mesh to conduct electrical currents, then you're usually working within electronics, like in telecommunication. You can see it in any kind of power plant. The medical field, it's kind of everywhere. It's even used in the aviation and aerospace industries for lightning protection. Pretty important. And the most conductive alloy you could use is copper. Now, technically, copper isn't an alloy. It's on the periodic table of elements right here. And metal alloys are when you combine multiple elements together, so literally not an alloy. But woven wire mesh can be made of copper, so we're gonna talk about it. Just to put into perspective, copper has an IACS rating of 100%. It's the literal benchmark for this kind of a thing. Aluminum, which is also known to be very conductive, only has an IACS rating of 61%. The only element that surpasses copper is silver, with a strange rating of 105%. Let's not think about that too hard. Silver woven wire mesh is very rare because it is obviously very, very expensive. And it's only 5%. Plus, making a transaction over 5% would weigh heavy on the heart. Segue. Weight and density. What about weight and density? It's aluminum, no contest. Now, of course, there's others, but aluminum is by far one of the lightest elements used to take off a few pounds. And since it's pretty dang conductive, it can be used a lot in electrical equipment, especially the portable stuff. And again, technically, it's not an alloy, it's an element, it's on the periodic table, but it's woven wire mesh. What do you want from me? Magnetic properties? Magnetic properties are sometimes really important in woven wire mesh, like an electromagnetic shielding. And yes, you can use non-precise woven wire mesh, but you won't nearly have the consistency that the precision woven wire mesh will give you. And you can also find this kind of mesh in particle separation. If the particle you're trying to separate is magnetic, why not have a mesh layer that's also magnetic? You can also find this type of mesh in MRIs, magnetic filters, and just general electromagnetic devices and equipment. So you get these magnetic properties from iron-based elements. And what is a commonly used wire mesh alloy that generally has the best magnetic properties? Stainless steel! Yeah! Yes! So what exactly is stainless steel? Stainless steel, baby. Its primary ingredient is iron, hence the magnetism. Then we have chromium, carbon, manganese, silicon, and a little bit of sulfur and phosphorus sprinkled on top. Now, I need to put a giant asterisk here. Stainless steel is one of the most customizable alloys in the world. There are so many grades of stainless steel. You want more corrosion resistance? Boom, there you go. You want more strength? Boom, you're welcome. They're throwing molybdenum in there. They're throwing nitrogen in there. They're throwing tungsten, niobium, copper, vanadium, and nickel in there. And nickel is what I want to talk about. If you add too much nickel into the mixture, it actually stabilizes the alloy and makes it non-magnetic. And two of the most common grades of stainless steel in woven wire mesh are non-magnetic, 304 and 316, non-magnetic. But another common grade of stainless steel that is magnetic is 430 stainless steel. And generally speaking, the 300 series is non-magnetic and the 400 series is magnetic. Not all of them, but generally speaking. And okay, fine, I'll say it. Stainless steel is the most common alloy in the entire world. Hands down, no contest. Ow. Edges are sharp. But that doesn't mean it's gonna win in any of the categories that we've talked about, except magnetism. Magnetism is pretty good magnetism. There's basically always going to be some other alloy that does the job better. But here's the thing, all right? We've been dealing in extremes for so long, but honestly, you don't always need the most extreme thing. Sometimes middle of the road is just fine. Stainless steel is an incredibly well-rounded alloy that can basically always get the job done, as long as you're not in a nuclear reactor or in the combustion chamber of a jet engine or submerged in sulfuric acid for hours on end. You know, normal stuff. But there is a secret second reason as to why stainless steel is the most common alloy in the world for woven wire mesh, and that reason is it's cheap. And honestly, that's kind of the crux of the whole thing. Yes, there are scenarios where you need Hastelloy, where you need Inconel, but those are specialty alloys that are way more expensive than common stainless steel grades. Stainless steel has them all beat, except technically aluminum. Aluminum is pretty cheap actually, but aluminum is just not going to cut it in most woven wire mesh applications. Stainless steel is more corrosion resistant, heat resistant, it's way stronger, just to name a few. At the end of the day, stainless steel is one of the most well-rounded alloys out there that is also incredibly common, incredibly cheap, compared to most alloys or elements that you could use for woven wire mesh applications. Now you might be wondering, what about brass? That is a thing. Well, it's pretty. No, it has its place, but it generally falls into the same thing as stainless steel, only worse. It's a little corrosion resistant. It's a fairly good conductor of electricity. It's non-magnetic, which can be very important sometimes. It does have this really interesting antimicrobial property, so it's very useful in the healthcare industries for medical equipment. It's used heavily in the particle analysis industry, mainly for those last 2 points actually. But ultimately, like any alloy, and let's say it together, it depends on your application. It depends on your application. And with there being so many possibilities for woven wire mesh, there could be a situation where almost any alloy of any grade could be necessary. It's really incredible actually, and that is why alloy is so important. It's actually this video that's the most important part of the woven wire mesh, not weave type, haha. Probably still weaves. Wow. That was a lot. That was alloys. Longest episode. A lot of words, a lot of content. But since alloys is over, that means... Thank you for watching the Woven Wire Mesh Masterclass. It has been so fun making these episodes. I really hope this has clarified things for you and given you an appreciation for woven wire mesh. It's absolutely crazy how woven wire mesh is literally everywhere and you would never know it. But it is there, and it's honestly doing a lot to make us live cleaner and safer lives. And again, thank you so much for watching. I'll probably make another masterclass on some other topic of woven wire mesh eventually, but these masterclass video things, they take a long time to make, so it'll probably happen, but it'll probably be a while. Maybe for particle analysis, maybe for filtration. Like and subscribe. But in the meantime, check out our other videos, check out our website with our learning center with written content on literally everything you can possibly imagine for woven wire mesh. Links are all in the description. And once again, my name is Andrew Kotlar. Thank you so much for sticking to the end, and maybe I'll see you around in another masterclass. Bye for now.